Next up, we have Max, who is a new professor at the University of California, Berkeley. He works on eGraphs and was one of the co-organizers of the eGraphs workshop that happened yesterday. Can we make him? And I was going to say something. Oh, so if you don't know what eGraphs are yet, that's totally fine. They're a very old technique kind of made new again by Max and others. He'll be talking about that, I'm sure, as part of this talk. And as a kind of fun fact, the first paper of my PhD actually built on a framework that Max released as part of his earlier PhD. So the first paper that I wrote was actually kind of related to this stuff. And Max will be generally talking about optimization and kind of a grand tour of what optimization in PL looks like. Maybe.
It was working? Okay, sorry. I jumped the gun. Cool it.
Let's try this one more time.
Pick a different one. I've got 4.
Ooh, you have 4.
Try this one. I don't know.
Can you check your display settings?
I mean, there's. Yeah.
Oh.
Do you see anything?
So you're not seeing one?
No.
Do you not have an HDMI port?
No, I don't have an HDMI port. I mean,
Can you just leave it?
let's try this one. Yeah, this one's working.
There we go.
Good enough.
Also, before you stop, can you take off your
I'm tethered in.
It's a topology puzzle.
All right. Now we're ready to go. Thanks for having me. I'm excited to talk about program optimization, a sort of unbelievably broad and deep topic. So I have 28 minutes now. So this is going to be a whirlwind tour, and I'm going to try to give a little, like a light taxonomy of at least some parts of this cool field that I'm finding interesting. And each part of this taxonomy, there's already been entire theses and careers sunk into. But that's okay. One of the things that I want to get across is that the PhD is obviously about depth, but breadth is cool too. And by finding buddies who know about these things and asking them what papers to read, I've had a lot of fun sort of dipping my my toes into some of these areas of other areas of PL, and we'll even get into a little bit of non-PL stuff about optimization. So let's get started. What's a compiler? Well, for the purposes of this talk, you're probably familiar with what a compiler is, but a compiler is anything that takes an input and produces an output, right? And in particular, we're concerned about constraining that output to have some relationship to the input. For a lot of purposes, for most purposes in this talk, that predicate might be equivalence, some sort of symmetric relationship, but it could be anything else. Maybe it needs to be lowered into some other fragment of the language or whatever it may be. And when we talk about an optimizing compiler, right, our job is a little bit harder. Right? We're now adding this notion of cost, as a property of the output, and now we're sort of doing an argmin, right? We want to consider all of the possible outs that are related to our input and find the one whose cost is minimized. And it's worth noting that when programming languages, when we talk about compiler optimization, program optimization, we typically mean minimized-ish, right? And this is interesting because when you use the term optimization in a lot of other areas of computer science or mathematics, they really mean optimization, right? They mean like if it's not the optimal thing, it's incorrect as an answer. And that's not typically what we mean. So we'll settle for minimized-ish. Okay, so you may have seen a picture that looks something like this when talking about like how to optimize a thing. So in sort of very vague terms. So we're writing a compiler, and this is our input, some point in this big cloud. All right, and this cloud is the space that defines all of the other programs that are related to our input in the correct way. Maybe it's, like I said, equivalence. These are all the equivalent programs, perhaps. And I've helpfully organized our cloud from left to right, where the better programs may be faster, maybe we're optimizing for code size or whatever the metric may be, are to the right. So the conventional and predominant and most effective and most used way that we're going to see, and we're going to talk about this more in detail later, to optimize these programs is basically about baby steps, right? We're going to use transformations iteratively, typically phrased as rewrite rules, to sort of iteratively change one program to the next, to the next, to the next, hopefully moving to the right along the way. Crucially, all of these steps stay within this cloud, right? Each of these steps is designed in such a way that it preserves whatever the property that we care about is, okay? And if they all go to the right and you do it until you can't do it anymore, then you've wound up to the right of where you started and you've optimized your program. Note that we may have hoped to sort of end up in this corner, which is, I guess, slightly better, but we wound up in this corner. And in this situation, there's nothing we could have done about that because we sort of did it greedily. Another way to wind up with an optimal program is to not do it iteratively starting from the program, but sort of starting from scratch. So you notice how I've changed the text up here from optimizing a program to building an optimal program. And this is a little bit of a different paradigm. One way to think about it is you're sort of approaching our cloud of acceptable programs from the side, right? So we're starting with programs that may not have the property that we are, or at least, they might not in and of themselves have the property that we care about just yet. But we can start by building up some small set of programs, and then we can compose them with one another, right? And this is a key distinction that I want to make, is when we are within this cloud, our sort of step in our search for an optimal program was transforming one program into another. And here our step is going to be composing programs with one another, enlarging this space until hopefully it intersects with our space of acceptable programs, all right? And this is going to be the sort of two approaches, the two schools of thought that I'm going to break down a little bit in this talk and give some examples for. The first I'm going to call transformation. And this is where we start with an acceptable program. Typically, it has the property that we care about, or it's close to it. And we build towards the good, right? We take baby steps, and those steps look like transforming an expression, transforming a term, typically with something that looks like a rewrite. The key questions we have to ask ourselves when we're designing an optimizer in this way is, well, what step are we going to take, right? At any given moment, we might be able to rewrite this plus to a times, or turn this division into a shift, or do something entirely different. And we might be able to do any of these things at many points in our program. Maybe it's a big program with a lot of additions in it. So which step do we take? Which one's going to get us to the optimal program, or even a better program? Likewise, you notice I'm sort of using the language of search here. We need to think about how do we manage our state space, right? You can sort of imagine about searching for an optimal program as sort of traversing a big graph where, one node is where you start, and if you take a transformation, you're sort of, taking an edge to another node. And this graph, in many cases is going to be infinite. So are we just going to sort of keep track of one node at a time, or going to, maybe you've written, Dijkstra's or A star or something where you keep track of a heap or something of the nodes that you want to explore from, something like that. And then the other paradigm that we're going to talk about a little bit today is called synthesis. Now, I call it synthesis to sort of evoke program synthesis, and indeed, I think, enumerative program synthesis, which you may be familiar with, is definitely within this school, but I want to take a broader notion of synthesis and really be thinking about any paradigm in which our baby step is composition rather than transformation, okay? So one way to characterize this set is you build up good programs, and you try to find an acceptable one, right? I think our picture did a better job than this, where we're sort of approaching acceptable programs starting from the good programs. Like I said, a key distinction here is that instead of transforming terms, we're composing terms. And this can be either bottom up or top down, right? If I'm trying to build a term, I might start from the bottom, start with my leaves like constants and variables, and then use connectives to build bigger terms. Or I might decide that, for whatever reason, the optimal program that the program that I want is a plus. Well, a plus of what? This is sort of top-down synthesis. I have plus with holes in it, and then I'll do some process to sort of iteratively figure out what I'm going to put in those holes. Likewise, we still have questions to answer, right? Which, this is sort of this sort of process, because we're composing terms, is sort of defined by our grammar, right? We're considering at every step, which term are we going to construct, right? Like, how are we going to come up with the next sort of problem, the next term that we're going to be considering. And likewise, this also has the same state space management sort of questions. Are we going to be holding on to one program at a time, or a small set, or all of the possible programs in sort of an exhaustive synthesis? These are all sorts of questions that we need to ask. And again, I've used this sort of phraseology to sort of evoke search, or sort of combinatorial optimization, basically graph search, if you're familiar with those sort of techniques. Because I think that while can be very expensive in a lot of in general settings, it's a useful perspective to think about program optimization. All right, so as part of our whirlwind tour, we're going to make it through sort of 4. I'm calling these algorithms, but they're sort of ways of approaching program optimization. On the transformation side of things, we're going to talk about sort of classical term rewriting, and again, this is a huge, gigantic field, so I'm only going to sort of skim over the surface of it. And we're also going to talk about equality saturation, which is closer to a lot of the things that I work on, which is also, I think, on the transformation side. And then on the synthesis side, I want to talk about an instruction selection algorithm. You may have seen this in compiler's class if you've taken that. And then we're also going to talk about query compilation. And query compilation, I mean SQL query compilation. So this is something a little bit outside of programming languages, but I think it's got optimization right in the name, right? It's got to be program optimization. And it has a very similar flavor, right? Like they have cost functions. They're trying to make the code go burr, right? Like these are the same kind of things that we want to do when we're building and optimizing compiler. So I think it's a great source of inspiration. And while I think that term rewriting fits solidly in the sort of the canonical transformation sort of approach, and I think instruction selection, as we'll see, fits squarely into this synthesis school of thoughts. These other 2 algorithms, quality saturation and query optimization, have a little bit of flavor of both. And I think that's one of the big takeaways that I want you to take away from this talk, is that this is not a strict dichotomy, and both the sort of transformative approach and the more compositional approach can definitely work together. All right, well, let's start with term rewriting, and we'll have to go a little bit faster, I think. So here's just an example rewrite to get a little bit of notation out of the way. If you've never seen something like this, we have a left-hand side and a right-hand side, and when we're doing this, we're going to look for instances of the left-hand side. All right, and so I'm using these lowercase x as a placeholder. So if I see anywhere in my program an addition, an add, where it's adding 2 of the same things, I can replace it with, well, a multiplication of that thing times 2. Okay, and maybe I want to rewrite that in the other way, but for now we're going to go this way. And so how do you do this sort of term rewriting? Well, if I want to apply some sort of rewrite that looks like the left-hand side to the right-hand side, if I want to apply it to a term t, well, I'm going to search for the left-hand side in t, and that yields a substitution, right? And this substitution is going to map the variables in the left-hand side to subterms of the term that I'm searching it in, of t. And then I apply that substitution to the right-hand side, filling in these holes, these named holes, with the subterms of t from the substitution. And then that's my that's my transform term. As I've phrased it here, we're sort of only doing term rewriting at the very top level, but you can also apply this to the subterms as well. Okay, so term rewriting, as I've sort of phrased it, is definitely the dominant form of program optimization. Like my web browser on my computer, on my operating system, we're all compiled by compilers that are predominantly using this form of program optimization. Peephole optimization, sort of going from one term to a slightly better term over and over and over until you can't anymore. All right, and there's a couple of reasons why this, in my opinion, this is such a great way to approach program optimization. Not the least of which, what I didn't write down, it can be made extremely fast, right? Your state space can be constant. You're only looking at one program at a time, and you take these rewrites, and there's all sorts of fancy algorithms to very quickly do this search part, and just make your program faster and faster and faster and faster. It's also modular and composable, right? So these rewrites are typically sort of objects outside the system, and you have a rewriting system that can accept any number of these things and apply them in sequence. And so if you have a bunch of rewrites and you want to add a bunch of more rewrites, you don't really have to change your system. And they're composable in the sense that if you typically want to prove about each rewrite that it preserves whatever the property that you care about from the left-hand side to the right-hand side. So if we care about equivalence, we want to show that, hey, if I ever apply this rewrite to a term, it's going to be equivalent to the thing that I started with, right? And inductively, no matter how many times I applied, no matter how many rewrites, I'm going to stay equivalent. I'm actually going to keep preserving my property. So that modularity and that composability are really great, and I think this is why this technique is so dominant. Outside of optimization, it's also used in theorem proving to solve something called the word problem. And if you're not familiar with that, it basically means, given some rewrites, can you get from some term t to some other term t prime? Okay, and that's undecidable. So what do we do? How do we actually approach this problem? Because your Z3s and all these other theorem provers, and in fact, inside your compiler, they're solving versions of this word problem all the time. So how do they approach that? Well, the way that ideally you would like to approach term rewriting is by avoiding search at all costs, right? Like as we've been phrasing it, you have these questions like, oh, I have this term and I can maybe rewrite it in all these different ways and take me to some other node in my optimization graph, and then from there go to another one, and that's an infinite graph. So it's no wonder that this is a super impossibly undecidable. But there are two key properties that if you can show this about your rewriting system, this lets you avoid search basically entirely, or rather reduce optimization to sort of a degenerate search problem where you just go straight ahead. There's no decisions to make. All right, what are those properties? The first one is termination, obviously sort of desirable. And basically what this is saying is that that optimization graph that I was talking about, that rewriting relation, there's no cycles in it, okay? And the typical way that you prove this, and this is going to smell a little bit like optimization actually, is that you show that if you can rewrite from t to t prime, then some cost, you make up some cost function, it can be whatever you want, it could be AST size, number of pluses, it can be something more complicated than this, goes down, right? And as long as it's going down, and it eventually, would hit 0, more or less what this means is then you can't have cycles in your rewrite graph, right? Because you're always going monotonically down, okay? And this is intuitively, I think, useful for optimization, right? Like if you're putting a bunch of rewrites into your p-pol optimizer inside of your LLVM or your GCC, you want to make sure that at least most of them are making your program better. Yeah, you can definitely imagine situations where you sort of want to climb the mountain to find a deeper valley on the next side, right? But then you have to start thinking about search again, right? And the whole point is we're trying to avoid doing that. Another useful property is that of confluence, okay? And confluence is the property where basically if you hit a fork in the road, if you can rewrite from t to t1 and t to t2, it doesn't matter which one you take, okay? Then that means that t1 to t2 will eventually rejoin in some other node later on in the graph. And together, these two properties allow you to sort of plow straight forward and not really think about, consider the choice of, oh, when do I apply which rewrite? It doesn't really matter. You're always going to, 1, stop rewriting, and 2, arrive in the same place. Like I said, your choice doesn't matter. But it's worth noting that you can still build useful things without these. I've been mentioning the sort of optimizers within LLVM and GCC and all these things, and in most cases, these properties have not been proven for those rewriting systems. They're probably pretty close, but these can also be sort of, manually enforced. If you are worried if your term rewriting system might not terminate, well, stop early. Just don't rewrite forever. If you're worried that your term rewriting system might not be confluence and you want to make it deterministic, well, just set explicit priorities. Say, we're going to do this rewriting system first, or this rewrite before this rewrite before this rewrite. A different priority system might end you up at a different place, but at least you have determinism back. Okay, so you could still build useful systems without these things, but if we can get them, we would love to. Okay, now to switch gears very quickly, we're going to move on to instruction selection. So we're moving on to the synthesis side of things to give a sort of canonical example of what these compositional algorithms can look like. So this is another problem from the compiler's literature. The problem, succinctly stated, is basically how we have an AST that represents our program, and we're sort of at the last step of our IR. We want to lower from our tree-based structure to typically a list-based machine instructions. Okay? And the other input, aside from obviously our program, is templates that tell you these possible lowerings. Okay? What do these templates look like? Well, you have some simple ones that don't do really anything exciting. If you see an add node in your AST, you could probably somehow emit an add instruction in your instruction set. Most have an addition instruction. But a lot of instruction sets have fancier instructions that do sort of many operations at the same time that ideally you would use because they can be faster, right? So in this example, if you see in your AST a store whose pointer is the addition of a pointer by the multiplication of 4 of some other thing, which this could easily be an array access or something, then we can, if you're familiar with x86 or something like that, you can get all of this from a single instruction that looks like this. Okay, so we would love to use these things when possible, but we can also use the simpler instructions when needed. Okay? How do we cover the AST with these templates? It's easier to see this pictorially. We have our AST over here, and we have our funny-looking templates over here. And the point is to literally cover the tree with these shapes, each one representing a template on how to lower that fraction of the AST into some linear ordering. And as you can imagine, you could approach this as a search problem. Well, let's just pick one and apply it somewhere. Let's apply the biggest one. We're going to sort of approach this greedily. If we take our biggest shape and apply it to sort of the obvious place here, then we're left with these two nodes, which we can cover with our sort of unit templates here. And that works, but this is a situation where the greedy approach does not lead to the optimal solution. As you can sort of see, the other two shapes are in fact the one that leads to the optimal solution. We can cover this tree with two shapes using the triangle over here and the sort of the bar over here. And the classic way to solve this problem is with dynamic programming. And so the way this works is, you're probably familiar with dynamic programming, is you want to basically divide and conquer the tree. And so the trick here is that there are many ways to divide this tree into a bunch of little trees. In fact, there's one for each possible location that we could, for each one of these shapes that we could apply at the root. So someone has to cover the root, right? So let's just pick one of these guys. Let's say the triangle, right? And that's going to cover the root. And that leaves us with a bunch of other trees. And this problem happens to have what's called the optimal substructure property, meaning that if we are assuming that the triangle is going to take the tile here, then the optimal solution with the triangle here is the triangle here and the optimal solutions of the trees, right? And so that is a classic tell that we're going to use a dynamic programming approach. So we're going to memoize all this stuff, and it's going to be super fast, and it's going to give us the optimal solution. Okay, so let's move on from instruction selection, but we're going to see some of those themes pop up later. All right, so now we're back on the transformation side of things, and we're going to talk about e-graphs. This is sort of the core of what I've been working on for the past couple of years. So let's dive in and see what the heck is an e-graph. Well, you'll see that it looks a lot like an AST. In fact, sort of any AST can be lifted pretty trivially to a sort of very, very simple e-graph here. But one thing to note is we've got two parts here. We have our sort of nodes, which are the nodes from your AST, but they're grouped into these e-classes or equivalence classes. And the point of this is that we're going to store e-nodes that we consider equivalent in the same e-class. Okay? Note that we don't really have any equivalences here because each e-class only has a single node in it. So how do we get more than one node into an e-class? Well, first I should introduce the notion of representation. So we say an e-class represents a term if you can sort of follow the edges and find that term within the e-class. So here we got this program a times 2 divided by 2. All right? And say we want to try to optimize this to a, right? We want to cancel out the multiplication and the division. Okay, so we're going to approach this, spoiler alert, via transformation, right? We're going to use rewrites to sort of iteratively grow this e-graph. All right, and this is going to look exactly like term rewriting, at least at the start. We're going to look for instances of the left-hand side inside our e-graph. Hey, I found one. It's highlighted in red here. It's our a times 2. That's going to give us a substitution, which we plug into the right-hand side, and so on. The difference is that instead of destroying this times and replacing it with the shift node, we're going to add the shift node to the same E-class. Okay, this is registering that, hey, I've learned now that A times 2 is in fact equivalent to A times 1, or sorry, A shift 1. And this is great because we've done the rewrite, we've learned the new thing, but we haven't forgotten the old thing, right? So what we're doing is we're taking term rewriting and we're shifting our state space. Remember I was talking about how much stuff are you willing to hold on to during a search? Here we are going to be willing to hold on to a lot more stuff. Now we're going to do our best to represent it compactly, but ultimately that's the trick we're playing, is we're growing our state space. So now this E-class represents A times 2 and A shift 1, all right? And the nice thing is that this notion of representation sort of bubbles up, all right? So you can see that this E-class over here, despite only having one node in it, represents 2 programs, okay? And I don't want to belabor the point here, but the point of the slide is that even if we applied this rewrite here, A times 2 goes to A shift 1, which, not a bad idea in general, but it is a bad idea if you're trying to reduce this A times 2 divided by 2 to A, because you sort of lost your multiplication, and it's going to be hard to cancel that shift later on. Even if we apply that, we haven't lost our handle on this multiplication, so we can eventually apply these other rewrites and prove that A is equivalent to our input. Okay, I'm just going to skip this slide for now. And the final component of this sort of algorithm, if we want to use this for optimization, is called extraction. And, well, we've made this big E-graph, but the point of program optimization is to have a better thing come out at the end of the day. And so we need to sort of do that last step. So we need to remember where we put our input. Somewhere in this E-class, our input is represented, A times 2 divided by 2. And here we simply want to pick the smallest member of that E-class. Now in this case, it's simple. We have the leaf A here, so it's not a whole lot to say. But in general, this is solved by a dynamic programming algorithm that looks very, very similar, actually, to the one that we saw before. OK, and so that's the equality saturation workflow. To sort of put it all on one slide, you take your initial term and you chunk it into an E-graph. It looks like that sort of basically AST-like E-graph that we saw on the first slide. And then we start turning that crank, okay? And here, when we do our rewrites, this is no longer well, it is a search procedure, but it isn't, there's no backtracking needed. You don't have to worry about taking a wrong turn because this is a monotonic process, okay? When we do a rewrite, we're only adding information. Our state space is only growing, and so the price is that our state space might grow a lot, but we don't have to worry about taking wrong turns. And then when we're done, we can extract an optimized program. And because we've only sort of taken steps that put equivalent things into equivalent E-classes, we have, in fact, you can generate a proof that the optimized term is equivalent to the input term. All right, so let's move on to the final step of our tour here, which is query optimization. And I thought I had animations on this slide, but instead you have to look at it all at once. So this slide is basically giving a very abbreviated version of what is called the volcano optimization architecture from query optimization. Now, don't worry if you're not familiar with SQL or databases or any of that, because we're not going to really even be thinking about it. I've sort of boiled it down to its essence here. And its essence is just a dynamic programming problem. But it's powered at the top level by rewrites, which I think is very interesting, and which is why I included it in my talk here. So let's take a look at this. So when we want to optimize some query, right? And for our purposes, we can consider a query a program, right? It's a thing that we want to make go fast, right? So that's what we're going to do here. So we want to optimize this query, and what are we going to do? Well, we're going to approach this with dynamic programming, so we need to figure out a way to sort of decompose this into smaller problems. Now, one way to do that would just be to look at the query and look at its children and optimize the children, and then put those right back as the arguments. But that's not enough because you might be able to transform this query at the top level. Okay? And so the first thing that the Volcano system does is it builds a set of possible rewritten queries. And so we're doing term rewriting here. These queries are exactly term rewrites that we saw before. And we're building all of the possible things that this query could be rewritten to, but we're only doing rewriting at the top level. Okay? We're not going to worry about rewriting the subterms because we're going to get there recursively. Okay? So, if we, changed from the language of relational algebra to, arithmetic or something, then, maybe the input program is, I don't know, A plus B, and one of our rewrites says that, hey, you could also rewrite that as B plus A, right? Or maybe reassociate those additions or something like that. Okay? So now we have all of the programs, the queries that have been rewritten at the top level. And then from here on out, this is just bog standard argmin, right? We're just going to loop over them. We're going to call optimization on the children and take the cost of the resulting query. And if it's better than the best one, update. So this sounds like a really simple algorithm. And I have bulleted it down a little bit here. But this is really the essence of the Volcano system. And this is more or less modulo a couple optimizations. The state of the art in query optimizations. So rewriting plus dynamic programming, if your cost function is friendly, if you're willing to accept some level of backtracking search in the sense that you are going to recurse on a couple different children here, can get you a long way and be state of the art depending on your domain. Okay. So just to wrap up, some of the themes that are exciting me currently in program optimization are basically these things I talked about. Thinking about program optimization, both in terms of the way that we think about it in terms of compilers, but also looking into other domains and being inspired by the sort of search phraseology. So program optimization is search. If you can avoid implementing it as a search, that's a really good idea if you can get away with it. But there's a lot of important contexts where you can't. Okay? And when you can't, you can look to sort of these two schools of building a search procedure, and in fact, you can combine them to build a really effective program optimizer. And again, the questions that you have to answer along the way can really result in vastly different looking algorithms. Are you going to only consider one program at a time or a many? Are you going to store these programs over space or over time, right? Are you going to have a set of programs like in an eGraph? Or are you going to have a backtracking search that sort of, maybe rewrites in this direction and then rewrites in that direction? And finally, one thing that I didn't get to talk a lot about is, well, optimization is about minimizing cost, right? And the properties of these cost function are very interesting and important and can change what you can do in your algorithms, right? We saw how in rewriting, these cost function can get baked in to your rules, right? Like you want to prove a term rewriting system terminating. Well, all of a sudden, now like the proof that your term rewriting system terminates takes into account properties about your cost function. And we talked about eGraph extraction just a little bit, but our dynamic programming algorithm for that only works for certain cost functions. If it doesn't have certain nice properties, then we have to resort to a much more expensive algorithm. So it's also worth keeping in mind the properties of these cost functions. Okay, that's all I've got. And just a quick shout out, because I didn't get to go to the earlier session. I am recruiting this year, so if this stuff sounds fun, I hope to see your application this cycle. All right, thanks.
Great, thank you. I think we have time for one or two questions.
Hello. Do you know about instruction combining or inst combining in LLVM?
Yeah.
Does this have potential to replace that huge pass, which is like handwritten optimizations for optimizing common patterns in terms that you see, like you showed?
Are you asking which one replaces which one?
No, can that complete pass be replaced by using this theory? Yeah.
No.
Okay.
I think, again, a lot of the algorithms in LLVM are designed for, to avoid doing search to some degree or to a great degree, because search is very expensive, whether you're doing it in space or in time. So this is definitely one of those cases where, hey, I would love it if we could cram eGraphs into LLVM, but the performance just isn't there yet because of how much stuff we're carrying around with us.
Okay. And another question was will this apply to maybe function calls? Like if you have a function which you pass parameter A and B to it, and you know that maybe the input to it is they follow an associative rule if you pass it. So can we apply similar stuff to function calls?
Sure, definitely. Yeah, I mean, those are part of your AST, right? And if you know properties about like, the function itself, then that might give you new axioms that you can use to optimize your programs. I mean, I think, extensible optimizers is one of, it's definitely like a holy grail of program optimization. And I think that's something that the query optimization people actually have figured out a little bit better. Their architectures for optimization are designed to be extensible in a little bit more easier way.
Okay, thank you.
Yeah.
Thank you for the talk. That does sound very fun. I wanted to ask, when you say that, is it ever useful to have negative values in the cost function? Like, can you think of scenarios where that happens? And also, I think that where it says that if the cost decreases each time, it's going to terminate. That doesn't seem true because if the cost halves each time, it's not going to terminate.
Yeah, so I was definitely skipping over things. It needs to be, a well-founded order, and then, there's all these sort of, sort of algebraic properties that it needs to have. But yes, so you can't, Zeno yourself. If you're doing integers, then you're good to go.
Okay, but are negative values, have you seen that as a practical, like, negative costs?
Sure. I mean, negative costs can pop up when, you're going to end up with something that looks very similar to negative costs whenever you have a composed program that is cheaper than any of its children, right? And so this is a non-monotonic cost function. And yeah, I mean, like, for example, the egraph extraction stuff doesn't work with that, right? That's one of the properties that you would really love to have in your cost function, but it doesn't always apply, right? And when it doesn't apply, you need to resort to fancier and more expensive algorithms all the times.
Thank you.
Yep.
All right, we're a little bit over time, so we'll wrap up. Let's thank the speaker again.